Hey everyone, welcome to week 4. Okay, so today I want to show you a little bit about a technique called Tf-Idf, but more importantly, I want to talk to you today about how we're going to teach computers to read. So computers are really good number crunchers, but they're not so good at reading words. So today we're going to send our computer to school and teach it how to read by converting words into numbers. If you've heard before the idea of language processing or text analytics, what we're going to do here is going to lay the foundation for being able to process textual data. This is something that's pretty cool and very powerful, and this is a technique used in the data science space very commonly. So in the last couple of weeks, we've been talking about how to use variables that are, structured or well known, right? So like back in the Titanic example, is the person male or female? Today we're going to use variables that are derived from text, and I'm going to show you how to do that. Okay, so first, just a quick little definition. Whenever we're talking about text, we talk usually about a corpus of documents. What the heck is a corpus? Well, it's just a collection of documents, just like a gaggle is a collection of geese. So I made 2 documents in my corpus. Document A, the cat sat on my face. Document B, the dog sat on my bed. All right. Usually when we're doing text analysis, we can use a model that's called bag of words to represent a document. And in the bag of words model, you can imagine that each document is really just a bag of words. And so that's what I'm doing here. I'm using the split command to split my my documents in my corpus into their individual words. And you can see that bag of words B is really just doc B split into words in a list. All right, so when we do this, this is called tokenizing. And there's a few different ways to tokenize. This is a very simplistic one. If you notice, all of my words are lowercase. There's no punctuation. There's no weird characters. That's pretty nice. In real world, it doesn't usually work out that way. Okay, so my split tokenizer works today in this simple example, so that's good. And we have these documents tokenized. But how do we get a tokenized bag of words into numbers? There are a few strategies. The simplest one possible, which I always like to start with, is to create a vector of all the possible words for each document and then just count how many times each word appears. So I'm going to do that here. First of all, I create a set of the unique words contained across all documents. I'm using sets here because that eliminates duplicates. And so I'm creating a union of the 2 sets, bag of words A and bag of words B. And that gives me a list, or actually, so that gives me a set in this case, but it's really a list of all the unique words in the corpus. All right. So then I'm going to create some dictionaries, one for each bag of words. And I'm going to set all of the values for those dictionaries to 0. So here's example word dict A, which is all set to 0. And then I just go through and I count all the words in my bag of words, and I increment the 0 by 1 if 1 is found. And so you can see here that word dict A now has a count, not a cat, of all the words that occur and their occurrences. So in word dict A, we can see cat occurs once, face occurs once, my occurs once, and so on. All right, so then lastly, what I can do is I can take those 2 dictionaries and I can stick them into a matrix. And here we have that matrix. I'm using pandas for convenience and for readability here, but you could just as easily use a NumPy array. And what this gives me is an example of a numerical representation of both sentences or both bags of words for the computer. And so the computer can start to, now we can build models to analyze all of these unstructured bags of words. And so just like that, we've converted a word problem to a linear algebra problem. And computers are really good at linear algebra, probably better than us. So that's great. Mission accomplished. But wait. If you notice this, my, on, sat, the, Those are pretty common words, and they all occur on both of these in both of these documents in the corpus. So the problem with the counting strategy is that we use a lot of words commonly that just don't mean much. In fact, the most commonly used word in the English language, the, makes up 7% of the words that we speak. And that's double the frequency of the next most popular word, which happens to be of. And that's double the frequency of the next most popular word, which I don't know. The distributions of words in language is called a power law distribution, which is the basis for Zipf's law. Here's the link in Wikipedia. By the way, you can get this document off of my GitHub. Okay, so if we construct our document matrix out of counts, then we end up with numbers that don't contain a lot of information, unless our goal was just to see who uses the most. All right, so that's where Tf-Idf comes in. And Tf-Idf is just a better strategy for counting words and weighting the counts appropriately. So rather than just counting, we can use Tf-Idf as the Tf-Idf score as of a word to rank its importance. So the Tf-Idf score of a word, W, is going to be the term frequency of the word multiplied by the inverse document frequency of the word, where term frequency is the number of times the word appears in the document, normalized by the number of words in the document. And inverse document frequency is going to be the log of the number of documents divided by the number of documents that contained in the word. All right, that sounds a little bit weird, but hopefully this example is going to work it out for you. I'm going to be implementing Tf-Idf in code here. Luckily for you and me and everyone, we don't have to do this every time we use Tf-Idf. Tf-Idf is well known and built into scikit-learn and Python and other places, and you'll be able to use Tf-Idf just by calling a library. But I want you to understand how it works, and so I'm going to work through some of the code. The first thing I'm going to do is I'm going to compute the term frequencies. And the way I'm going to do that is I'm going to implement this bit of code. I'm going to count the number of times a word appears in a document, and then I'm going to divide that by the total number of words in the document, and that's what this does. So then I'll calculate the term frequency for bag of words A and the term frequency for bag of words B, just like that. All right. So then moving on, compute IDF does the same thing. In this case, I only really need to compute the IDFs one time for all of the bags of words altogether, because IDF refers to the number of occurrences of a word across all documents in the corpus. So again, I just go back to my original definition up here. It's the log of the number of documents, n, divided by the number of documents that contain the word W. So, first of all, I figure out n, and that's just the length of the number of documents. That's easy enough. This next part's a little bit harder. To count the number of documents that contain a word W, I end up iterating over each document in the document list, and then each word, and then for words that exist, I'll increment them by 1. That's a good way to only count one instance of it. All right, and then lastly, I'll take what I had just calculated here, which I had stored in a dict, and I will take n, and I'll divide it by that previous value, and then I'll apply log to that, and I'll return that dictionary. And so that's my IDF value. All right, and then lastly, we're going to compute Tf-Idf, which is really just the Tf times the IDF part. So I've done that here. And then lastly, I'll stick those into a data frame. Now, this hopefully will show you what some of the power of Tf-Idf is. If you remember before, I'll scroll back up. Scrolling. You saw that the most common words were on, my, sat, the. And they didn't really provide much differentiation. We had two sentences that are very different, right? One's about a cat sitting on a face, the other one's about a dog sitting on a bed. If a computer were to look at these, there's some differences, but it's pretty hard to see. So down here in our Tf-Idf example, it's a lot easier to see. We can see that the words that occur commonly and equally across both documents in the corpus are 0. They're just not important. We don't care. But we can see that the first document has values to face and to cat, and the second document has values to bed and to dog. So it's very easy for even a human to see and for a computer to see that this one is all about beds and dogs, whereas this one's all about cats and faces, unfortunately. Okay, so that should give you a little bit of intuition on how Tf-Idf works and why it would be helpful. And next we're going to cover a use case where we use Tf-Idf to do some analysis, and I'll see you soon.